Good afternoon, everybody. Welcome to a sunny but cold Monday afternoon of Chem 170 with your host, me, Dr. White. Hi, everybody. All right, before we get into actual chemistry and stuff like that, yesterday, I think it was in the evening, there's a great program on the History Channel called Food That Built America. And they had one about peanut butter. I sort of knew about peanut butter, but I didn't realize how much chemistry and interesting it is. And the key thing, and let me get to my browser. They talked about Joseph Roosevelt Field, and he was a chemist in Kentucky who came up with the modern peanut butter we have. And he first came up with a peanut butter called Peter Pan. And I thought I had on there, here it says, and how did he come up with peanut butter that we now use? Well, before then, if you got peanut butter that they were trying to sell in the 1920s, you'd open it up and there'd be a layer of oil on top. And you go, I don't want to eat this. Plus, it would go bad. And what he came up with, and it was funny on the program how they butchered it, whoever wrote it wasn't a chemist, they hydrogenated the oil in peanut butter. And you know hydrogenation. The reason I'm bringing this up is I keep on telling you, why are you learning this stuff? And the real answer is because you want to get a good grade, because someone said you need to take organic chemistry. Well, why learn this? And you learn for test number 1. Take a excuse me, take a catalyst and hydrogen reactor with a double bond. Double bond has 1 pi bond, 1 sigma bond. You break the pi bond and you have a hydrocarbon if you start with an alkene. Well, last chapter, if this were an oil as opposed to fat, which tallow, white grease, yellow grease, we use SOS, is highly unsaturated. R-sub-O means there's a double bond in there. And if you fully or partially hydrogenate it, you can pick the catalyst, nickel, platinum, or palladium. Probably nickel, it's cheaper. Esters under these conditions will not react with hydrogen and catalyst. In fact, I'm not sure I've never done that, so I'd have to look up what conditions. I think you really got to go fanatic on it. But anyways, when you make fully hydrogenated fats or oils, you take the double bond R-sub-O becomes the sterile R-sub-S with a single bond where there was a double bond, carbon-carbon single bond. And these are usually solid or semi-solid at room temperature. Well, by doing that, you made the peanut butter more solid and it was more stable. By getting rid of the double bond, you can't react with oxygen and go stale, go rancid. How many of you have ever tasted anything that goes rancid? Yeah, that. But anyways, and it was an interesting story how this gentleman, Roosevelt, first came up with Peter Pan. The company that he went with, I forgot which one, turned around and ripped him off and let him go. And he turned around and said, all right, I'm going to make a better one than Peter Pan. He came up with Skippy. Now, the story gets more interesting because for many, many decades, Skippy was the leading peanut butter. And it's a huge industry. I didn't realize how huge, but huge. A lot, I don't know how many hundreds of millions of dollars. Well, in 1958, Procter and Gamble, who I worked with, but I was around working doing chemistry in 58. I was still in grade school. Oh, now you know how old I am. But anyways, I was just a little guy. But anyways, Procter and Gamble bought a small peanut butter company, and because of their experience in hydrogenation of fats and oils, they made Crisco shortening, which what is it made out of? Fully hydrogenated oils. And they knew how to hydrogenate. Well, the story got interesting that Procter and Gamble's new CEO wanted to spread Procter and Gamble out of just cleaning supplies and things like that, you know, like your soap, Ivory soap, and things like that, that he decided to buy this, and it was a big gamble. But because they knew how to hydrogenate other oils, they did that, and then they did something else. They made it super sweet, so kids would say, "Ooh, this is better than Skippy. I'll eat it." And they did, and it took on a dominant. It's since been sold to other people, other companies. But the reason I'm bringing this up is all of this is based on hydrogenation of a double bond. And by doing that, you made a better peanut butter. Now, the other thing Procter & Gamble did was they made it sweet as the heck. And kids said, wow, you show me a kid who doesn't like sugar. I haven't met one yet, including Dr. White. Now, I have to be honest, full disclosure, I don't like peanut butter. My two sisters loved it. I don't. My father didn't either. I wonder why I don't like it, but I never have. My father came up with a great substitute for a peanut butter and jelly sandwich, and he'd make me and himself, my sisters and mother were having peanut butter and jelly sandwiches, say for lunch. My mother decided to make that. He would make not peanut butter, cream cheese and jelly sandwich. Oh, do I love those. That's another story. And I thought I'd bring up something interesting about why are you learning this? It's played a big role in things in our daily life. All you have to do is go to the supermarket, look at the big wall of peanut butter in any supermarket. All right, let's get to organic chemistry and Chem 170. A week from this Wednesday, not this Wednesday, but a week from this Wednesday will be test 4. Look, I get that finger fixed. Test 4. And by Wednesday, I'll post what test 4, how many pages and everything, but I will tell you test 4, I got the finger fixed. Test 4 will cover just carbohydrates and fats and oils. That's enough. So I'll talk more about that on Wednesday. All right. Let me just close something up. But I find that it's on Sunday, they play older, and they usually have one newer episode. on the History Channel, Food That Made America Greater, something like that. And it's really amazing. Taught me a lot. All right. All right, now last week we started talking about carbohydrates, and carbohydrates, you should know, are polyhydroxyketone, polyhydroxyaldehyde, or a molecule upon acid hydrolysis or deshydrolysis becomes a polyhydroxyaldehyde or ketone. And here on your board, you see an example of that. And let me just close two more things. And this is glucose, and I'll talk more about it today. Now, we talked about chirality, handedness, and I hope you put your right hand up to mirror left hand, saw the reflection and say, ooh, non-superimposable mirror images. Now, I talked about enantiomers, and I thought I'd go back and cover this again in case I went through it too quick. And an enantiomer is a molecule with a non-superimposable mirror image of each other. And it's a word, one of the few words in organic chemistry I constantly spell wrong. So I'm going to cheat. So the question is, draw the enantiomer of the following molecule. And why don't you try that? What it means is draw the mirror image. We went through that, but I'll see if you remember. And I'm still fascinated in my mind about that great show last night on peanut butter. But if you had watched it when they started doing the hydrogenation, boy, did they, the visual they have and everything, boy, did they botch it. Because they had hydrogen looking more like a water molecule. I found that entertainingly funny. Everybody's done. My turn. Enantiomer means the non-superimposable mirror image. So here's my mirror. You don't have to do it, but I like to have my mirror here. it helps me do this correctly. So I have my backbone, my carbonyl, the aldehyde, you can write this way, or you can write the mirror image, but it's not a chiral carbon. I have these. Remember, every intersection of a line is a carbon, a Fisher projection. The bottom one is a chiral. You can write it that way. If you wanted to write it this way, you could. Actually, to be honest, the two would have to be on that side, but anyways, we're talking about hydrogen, it's not a number. So this carbon right here, the hydrogen is closest to the mirror. That's what you'll see first. Farthest away, hydrogen. Second carbon, you'll see the hydrogen close to the mirror, the hydroxyl group farthest away. And the third carbon, hydroxyl group close to the mirror, hydrogen farthest away. And that's how you draw an enantiomer. Oh, let's do another one. These are fun. And I've drawn, hopefully I did it correctly. I'm pretty sure I did. Which you don't have to know the structure, but I thought I'd write it down. Glucose. Draw the enantiomer of glucose. And for those of you who are picking your web camera on, thank you. And for those of you who have finished, be patient. I try and give everybody time to finish. Finish. All right, my turn. What is the enantiomer? How do you draw it? Oh, it says it right there. Someone was nice to print that out. Hey, oh, it's awful Monday, bad humor day. All right, non-superimposable mirror image. That's the enantiomer. You don't have to, but I'm going to put it in my mirror. And I'm going to have my backbone. 1, 2, 3, 4. The aldehyde at top, the CH2OH, a chiral carbon. Oh, I gave it away. What's closest here? Hydroxyl group. So you'll see that first. And the hydrogen here. Same thing for the next one. Now here, the hydrogen is close to the mirror. So you'll see that first in the reflection. You'll see the hydroxyl group farthest away. And the last one of these carbons, hydroxyl group is closest, hydrogen are farthest away. Now, that's how you do it. But while we have glucose, I'm going to write it again. And now what I like you to do is Circle the chiral carbon atoms in glucose. I don't know, 3 points each. If this were part A, remember, every intersection of a line is a carbon. I don't know if I told the story, but first of all, I think it was Saturday. Look out the window. Or was it Friday or Saturday? I think it was Saturday. And what was happening by my house? It's snowing, light snow, but it's April. It's the end of April. And it reminded me back when I was a junior in college, I think it was 1967. Wow, it was a long time ago. But anyways, on April 14th, the day before when taxes were due then on the 15th, we had 14 inches of snow. And the next day it melted. So the floods, they extended the date for the taxes being due in Chicagoland by 1 day. All right, let's take a look at this. How do you know what is a chiral carbon? It has 4 different groups, 4 different atoms, or a combination of 4 different groups and atoms on it. If a carbon has 2 or more of the same thing as out, if it's in a double or triple bond, it can't be chiral, it's out. Now, let me remind you, what does that mean? It's an aldehyde, which sugar chemists write it this way. Synthetic organic chemists, even though I'm talking like sugars, I'll write it like a sugar chemist, write an aldehyde this way. We show the carbonyl, the double bond, because it's cool. But anyways, so this carbon can't be chiral because it doesn't have 4 different things. So this is out. This carbon right here, it has 2 hydrogens. It needs 4 different things. It's out. So we now have these 4 carbons. And I'll only do one because they're all chiral. You should have circled all of these. And if we look at this carbon, it's got this aldehyde. Oops, all this I'll call our hydroxyl group and hydrogen. That's 4 different things. And if you do the other carbons, excuse me, I think I got a frog or something in my throat, ribbit. But anyways, it has 4 chiral carbons you should have circled. Oh, let's do one more. And why don't you circle the chiral carbons of this new molecule I just made up? I don't even know if it has a name. Probably doesn't. One thing I should point out, I could have also written it this way. And this is the same molecule. I'm just not showing the carbonyl carbon. Ooh, I just thought of something. 6 months ago, if I said carbonyl carbon, would you even know what I'm talking about? Probably not. Think about how much you've learned in our short time together. Aren't you proud of that? You should be. All right, let's circle the chiral carbons. All right, anything that's in a double bond or has two or more of the same thing atom is out. So this carbon is in a double bond. Same thing for that carbon. This has two hydrogen. This has two. Ooh, and this carbon has two hydrogen. So that leaves us this carbon and this carbon to consider. How many of you got fooled by that one? See, Dr. White can be sneaky. All right, let's do this carbon. Hydrogen hydroxyl group. This I'll call R. And this whole thing I'll call R prime. And that's four different things or groups. R prime, hydrogen hydroxyl. So that's a chiral carbon. Let's look at this carbon. Hydrogen hydroxyl group. The CH2OH, let's call that R. And the rest of this right here, I'll call R prime. So if we look at this carbon right here, hydroxyl group, hydrogen, R prime, four different groups, four different atoms, in this case, a combination. So this would be a chiral, which meant this carbon and this carbon, same thing. And that's how you do enantiomers, and that's how you also do chiral carbons. Skills you need to know. Hint for test number 4. I gotta get that fixed one day. All right, let's move on to some new stuff. I talked about diastereomers, like those are stereoisomers whose molecules are not mirror images that will not be on its test. All right, I talked about Fisher projections. I used to put this on a test, take this molecule, make it into Fisher projection. Everybody got that wrong because most of you have trouble seeing and rotating things in 3 dimensions without models. Sometimes I do too. But remember, you rotate it, flatten it, and that's how you get it. Now, in a Fisher projection, just to remind you, E and C are coming towards you, and D and A and D are going back. Hold on, time out for let me get something. And if you think of E as red and C as yellow, it's time for Dr. White's 3D TV. Got to put on your special light now. But see how this is coming towards you and the red is going back away from you? And a Fisher projection, you rotate it, then squish it flat. So it looks like it's flat, but it's really 3-dimensional. And Emil Fisher had helped organic chemists with sugar chemistry. This will not be on test. All right, now, a couple things I'm going to cover next couple slides. Click, the switch will be off, but if you take any kind of other classes where you should know about carbohydrates, this is important things you should know for other classes, not mine. Now, for nomenclature of monosaccharides, that's a simple polyhydroxyaldehyde or ketone, of sugar chemists or carbohydrate chemists came up with what's called DL designation. And what you do is, and this will not be on test, but for other classes, you may need to know this, so I'm going to tell you about it. The chiral carbon with the highest number, if the hydroxyl group is on the right, is D. If it's on the left, it's L. Now, if we look at this aldehyde, carbonyl carbon is 1, 2, 3, 4, 5, and this is carbon 6. Now, carbon 6 has 2 hydrogens, so it's not a chiral carbon. The highest number chiral carbon is 5. And because the hydroxyl group is on the right, this would be a D if we're on the designation. Here, if we're on that on the left, this would be L. And I think D's is shorthand for dextrose and L levose, which I think, and I'm not, don't quote me on this, is right and left in Latin. No, I don't know Latin, but I believe that's correct. Now let's go out in the real world and see something interesting. And we had Sigma Aldrich, and Aldrich, before it was bought by Sigma, is probably the best. Where did I lose you already? There you go. Probably the best chemical company or supplier of small chemicals in the United States, if not the world. And here they have another structure I'll talk about. They call dextrose, but notice it says D plus glucose. And that D tells you the hydroxyl group on carbon 5 is on the right. Now, interesting story. Oh, I got a lot of stories I can tell you. I've done a lot of things. But anyways, I was teaching Chem 1 70 years ago. And one of my students who was a nurse going back to get her master's degree in nursing said, oh, that's why the D is on the bottle of glucose we use to do intravenous feeding, you know, putting in sugar to help patient get nourishment. And that D was on there. And all that tells you is that carbon, the highest chiral carbon, has the hydrox group on the right. Now, let's talk about, and switch still off, but this is stuff you might want to know for other classes that you might be taking or will take. And that's when we talk about physical properties of carbohydrates, or especially enantiomers. Now, enantiomers are non-superposable mirror images like your hands. They are identical in all their physical properties, color, melting point, and things like that, except for sometimes key physical properties. For enantiomers of sugars or monosaccharides, the only things that are different is their optical activity and the reactivity of other chiral carbons or molecules. What's optical activity? Well, optically active compound rotates plane polarized light, again, switches off, click, when you pass it through it. No, I don't have a slide for it. If you look on your screen on the right, you'll see this very pretty colored. This is unpolarized light, and it comes to you as a wave. Now, the wave can be this way, or this way, or this way. All 360, I only show a couple ways of the compass. The light, like the white light in my room from the light bulbs or the sun. Now, if you have a special filter called a polarizing filter, depending on which filter, it will stop all light except for one wave, which is what they're showing you, and that's polarized light. How many of you have ever heard of polarized sunglasses? Well, they're letting through only one wave, so they're cutting out a lot of the other energy, light coming to your eyes, which is why they work. Now, if you put plain polarized light through certain chiral molecules, sugars, it can rotate. Say the plain polarized light was like this, the plane's coming at you. It can rotate it to my right, so many degrees from 0, or to the left. And if you take a sample of a chiral monosaccharide or sugar, it will rotate to the right or left. And at a different temperature, a certain temperature and concentration, it's always that same rotation. And you can use that to identify purity, which is a good thing. Now, if it rotates to the right, my right, it's got a plus sign they put in the name. If it rotates to the left, it's a minus sign. Again, switches off for this. I'm doing a lot of hand signals. Anyways, I couldn't resist. But the only way you can tell, will a molecule rotate plain polarized light to the right or left, is go in a lab and shine light through it. There's a device that measures that plus the degrees. You can't look at the structure like you can for D or L. Now, the other thing is how it reacts with chiral molecules, other ones. Think about, well, hold on. I still have my car keys and everything. Wow, look out. I have a lot of, not many, I've cut back. But here's my house key. Oh, I better hide it. Anyways, if I were to put it in the lock upside down, it won't go in. You've got to have the right orientation for it to work, to go into the lock, let alone open the lock. Well, it turns out, let me put my keys back in my pocket. It turns out molecules that are chiral interact. They have to be the right chirality to, just like I'm pulling my hands together. And that's one of the reasons a lot of pharmaceutical products are expensive, because you have to have the right enantiomer or it won't work in your body. And like I said, if it's dextrorotary, rotates plane polarized right to the right, it has a plus sign, lavatory, rotary, I don't know how to pronounce that, but anyways, it rotates it to the left. And you see a minus sign. If you remember what I showed you, the dextrose or sucrose glucose they were selling was D plus glucose. That meant D, the hydroxyl group on the highest chiral carbon is on the right, and plus it rotates plane polarized light to the right. All right, let's go back to chapter 16. And one thing I got to turn off so you don't see all these lines, because Microsoft Word doesn't like chemistry words unless you load them into the dictionary, which if I were at a school like ECC, it won't be. All right, now let's talk about some things again. Right now, switches in the off position. But again, you might need this for other classes. Now, when we talk about monosaccharides, carbohydrate chemists come up with different classifications, and those are, one is aldoses. And an aldose is a monosaccharide that contains an aldehyde. And here's glucose, and there's our aldehyde. Remember, this is the same as this. And so this is called an aldose. Now, if you have a ketone, isn't it amazing? You know this stuff? You know what a ketone is? We played that fun game, circle and name the functional group, 2 points each for test 2. Here, you have a ketone, and this is called a ketose. And ketoses are monosaccharide that contain a ketone group. Now, how many of you heard of ketosis? That's something diabetics have to be very careful about. And what was that? 4 summers ago, when I teach face-to-face, especially during lab, I tell students, one, if you have any medical condition I should know about, if you have a problem, see me in private and tell me how I should handle it. I've had students who have been epileptic. Luckily, they haven't had seizures, but they told me what I should do. Even though I thought I knew what the right stuff is, I'd rather learn from them what the right stuff is. And turned out that summer, I had 2 students who are diabetic. How did I find out? Because it was pretty, not new, but still I wasn't aware of it. They had the patch on their, it wasn't a patch, the little pump on their arm that would inject, I guess, insulin when they needed it. And they knew all about ketosis, unfortunately. All right. Now, click is on, switch is on, click. Sugar, you've heard that all the time. What is a sugar? It's a designation for a mono or disaccharide. So if we talk about glucose, that's called a sugar. If we talk about fructose, that's a sugar. Now, the one you're most familiar with is sucrose, otherwise known as table sugar, or just sugar in our daily life. If you're in a restaurant, you ask the waitress, could you please bring me some more sugar, the little packets. I haven't been in a restaurant in ages that has the container you pour it out of, but this is, like I say, a sugar. And this is the designation for mono and disaccharides. Now, right now, I'm going to turn the switch off, but later on, I'm going to talk about this equilibrium that you see on your screen. Let's talk about important monosaccharides. Probably the most important one is D-glucose. It's the most abundant sugar in nature. And later in the chapter, I will teach you why it's the most abundant sugar in nature. It's a sugar because it's a monosaccharide. It's an aldose, it's got an aldehyde, it's got 6 carbons, and it's got 1, 2, 3, 4, 5 hydroxyl groups. Now, it's the sugar that's in our blood that helps, and now I'm way beyond my knowledge of the human body, but it helps bring nourishment. Now, this part you don't have to know. It's called an aldohexose, the hex meaning 6 carbons. And it turns out, just like you saw in the Aldrich web page, it's a plus D glucose. That's the sugar that's in our blood, and it rotates plain polarized light to the right. That you don't have to know. But you should be familiar, especially it's the most abundant sugar in nature, and it's the sugar in our blood. Now, D-fructose, again, switches off, but we'll talk more about it, is this compound. It's also a sugar. It's called a ketohexose because it has 6 carbons. Now, it turns out fructose is the sweetest sugar we know of. Let's find out something real quick. And fructose is about twice as sweet as glucose. And let's do one more, which I'll talk about later on. And fructose is about almost twice as much. They have a range here, but it's similar, twice as much. Now, fructose rotates plain polarized light to the left, but it still has a D, because this hydroxyl group, the highest priority chiral carbon hydroxyl, is on the right. Now, years ago, organic chemists found a way of converting corn syrup and also growing and converting it into high fructose corn syrup. And it's time for a break, so you're going to have to wait until after the break to learn more about fructose. So let's take a 5-minute break, and I can get up and stretch. All right, I got a computer problem. I got to figure out what this was. Hold on. There we go. I don't know why that happens. Any of you computer experts out there? Let me open up some things here. All right, we're back on track. Sorry about that. I don't know what happened. My computer burped on me. Anyways, we're talking about fructose. Now, fructose is the sweetest sugar around. And I don't know if you can see it. Let me make sure you can. All right, everybody see the ingredients label of Coca-Cola? And right here, carbonated water. And there you see high fructose corn syrup. And that's there to make it sweet. Now, many, many years ago, that used to be sucrose. Let's see if we can see it in the 1960s Coke. See where it says sugar here? And that's sucrose as opposed to fructose. And they found a way, organic chemists, to make high fructose corn syrup. And that's what they use. Now, I'll talk later on about if you've been following the last 15 years or so, and I sort of noticed that some organic chemists, a number of mothers groups have been rightly, I believe, but for another reason, I'll talk about it later, talking about how high fructose corn syrup in many products for children, and us too, but really children, cause serious medical problems like autism. That I don't believe, but I'll talk more about it. But it does cause serious medical problems like being overweight. So let's get back to our slides. All right, so we have deep fructose, and it's a ketohexose. Like I said, it's the sweetest sugar available, and it's found in corn syrup. I won't ever ask that on a test. Now, it also exists in the cyclic form, which I'll talk about. Now, it turns out sugars, and I'll explain this in a little while, can form a cyclic or ring form. And to show this, a chemist, Dr. Hawthorne, came up with what's called the Hawthorne projection. And again, it even says not on the test. Now, the Hawthorne projection is a two-dimensional structural notation that specifies or shows three-dimensional structure of a cyclic form of a monosaccharide. And here's an example on the right. Do not write this down. Years ago, and I've been teaching Chem 170 long enough, and the equivalent at College of DuPage, I tried teaching this to students and it was a disaster. And even I have to be careful when I work with Hawthorne projections. Now, these dark show it's coming towards you. And then like this hydroxyl group, the hydrogen, and I don't teach it in this class, it's called equatorial, coming this way, and the hydroxyl group is down, called axial. Again, I don't teach that in this course, but I found a way to get around how to use cyclic forms without the Hawthorne projection. Now, let's talk about hemiacetal and hemiketal forms of glucose and fructose. In order to do that, I need to talk about something you learned a long time ago. A long time ago, test number 2, you take an aldehyde or ketone, react it with an alcohol, look at the carbonyl carbon, what's attached to it. Is still attached to it. This part goes there and you get a hydroxyl group and you form a hemiacetal or hemiketal. Now, normally I'd write the CH aldehyde here like this. But for right now, I'm going to write it like a regular organic chemist would draw an aldehyde. Now, in the molecule, the reaction here, this is a intermolecular reaction. If you are going on an international flight from O'Hare, which I have done many times, you're going outside the country. It's 2 separate places, one inside the United States and one outside. Well, intermolecular reaction is between 2 different molecules. However, I'm going to show you an intramolecular reaction where everything happens in the same molecule. And because of that, you don't need a catalyst many times, and it's an equilibrium. It can go back and forth. It just doesn't go one way. Now, let's take a look at, and this is glucose. And I better be subtle. Oops, where's my red pen? Hint. Know this equilibrium. All right, now the carbon that has the hydroxyl group, that's this alcohol, that will attack this carbonyl to form this molecule here, and this bond is always C5. This hydroxyl group right here. And just like up here, this attacks here. This attacks this carbonyl. Now, instead of drawing a Hawthorne projection, which confuses students, I came up with an idea. That idea was, why don't we just draw the longest oxygen carbon single bond? It may not look pretty, but it gets the job done. Now, anything that's not involved in the reaction will not be changed. So what I'm writing are all the atoms and carbons that are not involved in the, oops, not involved in the reaction. It's only this carbon right here and this carbon. Now I have this oxygen, and notice it's going to be bonded to the carbonyl. So here's the world's longest and ugliest carbon oxygen double bond or single bond. And now, what's on this carbon right here? Well, if we look, and hold on while I move something out of the way, we look up a little here, it's got a OR, this oxygen is this oxygen. This R group is this carbon, and the rest of the sugar, the glucose molecule. And on this carbon right here will be a hydrogen and hydroxyl group. And you should know how to do this. On a test, if I give you the structure of glucose and this double equilibrium arrow, you should know how to draw the structure for the cyclic form of glucose. If I put the cyclic form of glucose, you should know how to draw the structure. You can put down the name too if you wanted to. I'll be nice on that. For glucose. And let's go through this again. You have an aldehyde or ketone reacted with an alcohol and acid. This oxygen attacks that carbonyl. What's attached to it? Our prime or hydrogen, and this should be our double prime, sorry, will still be there. That carbon, which is this carbon, the carbonyl, will have a hydroxyl group and an oxygen R. And this carbon is my R. Just so happens R and our double prime are connected together through the ring or the sugar. Now, I'd like to ask you to consider the following. Which is easier to visualize and see what's happening? This or this? This is the same thing. This same hydroxyl group attacks the carbonyl. Now, this carbon right here has the oxygen, and it's this carbon is the carbonyl carbon, or was. Now, which is easier, this way to see what's going on, or this way? I can tell you, I don't know about for you personally, but from test scores, from when I did it before and after, this way that I came up with is much easier. Now, if this doesn't happen, we won't have table sugar. If this doesn't happen and isn't available for glucose to form, we won't have any of the starches you know in your daily life. You know, the good things like French fries, pizza, bread, noodles, rice, potatoes, that wouldn't form. Also, if you look outside your window and you see grass or trees or anything made with cellulose, that wouldn't happen. So this is a very important reaction. Let's go through it again. You have this hydroxyl group, and the general reaction is ketone or aldehyde reacting with an alcohol. Now, since it's a intramolecular reaction, you don't need the acid catalyst like we do for an two separate molecules reacting. And this attacks the oxygen, the carbonyl carbon. What's attached to it, our prime or hydrogen. In case of glucose, our prime is hydrogen, our double prime, OR, OH. If we go back to glucose, always the C5 carbon. Remember, the carbonyl carbon is one. Each one of these intersections is a carbon. This hydroxyl group attacks the carbonyl carbon to form this carbon-oxygen bond, which is the same as this one right up here. And this carbon is the R group, everything. And this opens up to the hydroxyl group and the hydrogen, because R prime is hydrogen. And you should know how to do this. Now, I'm going to sort of cheat because once in a while I do fructose wrong, or all right, let's look at fructose. Fructose does the same thing with the same hydroxyl group on C5, but the carbonyl is a ketone. And here's the Hawthorne structure. Guess what? We'll use my longest and ugliest carbon-oxygen double bond to make it easier to see how this goes from here to here. This is the structure of fructose. It's got a ketone here. Carbonyl, carbons here, carbons here. Remember, every intersectional line is a carbon. And the general reaction I'll be showing you, I've just showed it before, but I'll put it up here again. With a intermolecular reaction, we'll do an intra. Now here again, oxygen of the alcohol attacks the carbonyl carbon, opens it up to the hydroxyl group in OR. Now in the fructose, R prime is carbons. And the hydroxyl group alcohol is still C5. This is 1, 2, 3, 4, 5. C5. Oops, didn't want to do all that. Come back. Now, once again, this is equilibrium because you're not using a catalyst, and the hydroxyl group on C5 now attacks the carbonyl here. What's unaffected, not involved in the reaction, won't change. All right, what will change is this carbonyl carbon, which is this carbon. And what do we have on there? OH. And then we have the bond to the R group, which is C5, this oxygen. And that's this right here. And this is the cyclic form of fructose. And if I give you the structure of fructose, you should know, if I ask if the reaction product or products are the following, and I give you this structure and this equilibrium arrows, I do it nicer. Hold on, let's see if I can do a nicer one. Well, my software does nicer ones. That's nicer. You should know how to draw this cyclic form. If I give you the cyclic form, you should know how to either draw the structure or write down fructose. Now, how can you tell the difference between the two? The carbon with the two oxygens in glucose cyclic form is carbon number 1. The carbon in fructose with the hydroxyl group is carbon number 2. And that tells you if it's on number 2, you're going to start with a ketone. The second carbon, if it's on number 1, the hydroxyl group, you're going to start with a aldehyde, glucose. And you should know this. And I didn't put it here, but you should know that. And we'll come back on Wednesday and I'll do this again, because I think this is so important. If this reaction didn't happen, along with the previous one, we wouldn't have any sucrose, table sugar. Now, let's talk about reductions, which is hydrogenation. I keep on clicking on the wrong thing. Zoom's come up with something new, and I haven't learned how to turn it off. My bar, you don't see, but I do, where I can click on the different things, disappears, and I got to click on that. Sometimes when I click on that, I click on the wrong thing. All right, let's go back and cover a reaction you learned for test 2. By the way, switch is on for this, just like the previous hint, know this. And you learn for test number 2, you have an aldehyde or ketone. When R prime is hydrogen, it's an aldehyde. When R prime is carbon, it's a ketone. React with hydrogen and catalyst. Remember, catalyst can be platinum, nickel, or palladium, or nickel, platinum, or palladium. This has got a pi bond. And you break that pi bond. and you make an alcohol. Now, you know something I haven't been sharing with you people? Again, this is glucose, and I'll never ask you to draw the structure in a nomenclature question on a test or the final. But if you take glucose and react it with hydrogen and a nickel catalyst, what would be the product? 3 points each. While you're doing that, I've got to find something. So let me find something. All right. Let me check and see if everybody's done. While you're doing that, I was multitasking, which I probably didn't need to, but I did it anyways. And when you're done, don't forget to vote. Now, I will tell you this, hydrogen and a catalyst will not react with an alcohol. Hydrogen and a catalyst will not react with a hydroxyl group in alcohol. And everybody's done. So it's my turn. What do you see that's different? Well, you got a bunch of alcohols, but what do we have here? An aldehyde. It could have been a ketone reacted with hydrogen and a catalyst, and the pi bond you'll break, and each atom of the double bond, carbon oxygen, will get a hydrogen. Well, guess what? Here's my aldehyde, and it's really this. So what's not involved in the chemical reaction I will rewrite because it's not going to change. Now this carbon, I'll break the pi bond. There's already a hydrogen on there, and each atom gets a hydrogen. Now I can rewrite this. This carbon has how many hydrogens? 1, 2. And notice we have this molecule. These are both identical. 3 lines means identical, not equal. And it has a trade name or a common name. It's called sorbitol. Now, one of the questions I've been asking, I haven't said in a while, is why are you learning this stuff? Well, we did with the peanut butter. And the obvious answer is because somebody said you need to take this course to get in a program or a school. Well, why learn this? Well, if I take glucose, which is the most abundant sugar in nature, I can get a lot of inexpensively. I react it with hydrogen and catalyst, I'll make this molecule, which is a 6-hydroxyl group alcohol, hexaol, I guess you'd call it. Well, what's so important about that? Well, sorbitol, and here's a way of showing sorbitol with the chiral carbons, and that's what the dash and wedge mean. It's the same as what I drew. And sorbitol is a sugar. It tastes sweet, but your body really doesn't metabolize it quickly. If you look here on the Wikipedia, it's obtained by reduction, which is another way of saying hydrogenation of glucose. And most sorbitol is made from potato starch, which can be broken down to glucose. And where is it also found? In certain things like prunes, peaches, and other things. But here's the interesting thing. A lot of over-the-counter drugs like cough syrup has sorbitol in there. Why? Because it makes it taste sweet. And if you're giving it to a kid, it tastes awful. But no, sorbitol makes it taste sweet. And now kid will say, all right, I'll take it, or you will. But because it's slow to metabolize, it has almost 0 calories. So why are you learning these things? Because they're used in your everyday life. Now, what's on the switch, on the slide, I'm going to turn the switch part of it off, the names, or sugar chemists or carbohydrates come up with interesting names. And one is called the glucoside formation. And the monosaccharides that I just showed you, the cyclic form, can form acetal or ketals with other monosaccharides. And those are called glycosides. Again, these names switches off, click. Now for glucose, the glucoside is the glycoside formed from glucose. And then a note for Dr. White, remember the reaction with methanol. Now, since it's going to take a long time, I think this is a good time. Let's take a 5-minute break, and then I'm going to go through all of it. I don't want to take a break halfway through in about 10, 15 minutes and say, all right, let's stop and let's get back to it. Let's take a 5-minute break now, and I'll see you in 5 minutes, and we'll go into how starches are made. Let's get going. Took about a 5-minute break or so. All right, let's get going. Everybody back? Now, what I like to talk about now is, thank you, Charles. And that is, I said no new reactions. Well, I sort of told a fib, a little lie. Let's go back and look at a reaction you learned for test number 2. Let me try and remember it. S. All right, keep your eye on the carbonyl carbon. You have 2 alcohols, and you form to that same carbon 2 OR groups. Now, what I didn't show you, and this won't be on a test, but I want to show you to help you understand something, and that is, if we look at the mechanism, not a full-blown mechanism, but a step-by-step. You have 2 alcohols, acid catalyst. You learned this reaction, same test. But now what you didn't know was this hemiacetal or hemiketal further reacts with the second alcohol to replace this hydroxyl group with this. Now, if you look at this molecule that we made, both R groups on the oxygen are the same. It's symmetrical. Well, it turns out that you can take this hemiacetal or hemiketal and react it with 1 alcohol to form it, and then a separate alcohol, R triple prime, to replace this. To form this new hemiacetal or ketal that's now unsymmetrical. I think I'm spelling unsymmetrical correctly. And I told you I was first one down in spelling bee always, and probably still would be. All right. Why is this important? Well, this molecule right here, we see in the cyclic form of glucose, where this R group is connected. So let's look at this. This is the cyclic form of glucose. And I showed you how to do that earlier. Let's see if it's still on here. Right here. This is a cyclic form. And what this really is a hemiacetal. I'll slow down. And now, if I react this with an alcohol and acid catalyst, otherwise known as an enzyme, most enzymes are really just fancy. This hydroxyl group is this hydroxyl group. Notice this carbon is this carbon. And you'll replace the hydroxyl group with OR triple prime. So everything that's not involved in the reaction, I can redraw. Everything that's not involved in the reaction, I just redrew, because you don't break carbon-carbon single bonds. And there's still a hydrogen here. The only thing that changes is this becomes OR. Let's go through it again. Here, you learn aldehyde or ketone, two alcohols. You form the acetal or ketal, which I never asked you to learn the names, but I use them. And the R groups are the same on the oxygens, so it's a symmetrical. However, if you look at the mechanism step by step, you go through the hemiacetal, or the hemiketal, and this hydroxyl group reacts with the second alcohol. Well, if you can isolate, which you can, the hemiacetal or hemiketal, which you learn this reaction, forming it with this one alcohol, you can use a different second alcohol to make an unsymmetrical. And that's what we're doing here. This is a part of the semester you got to be patient, because it takes me a while to draw these things. And I'll be patient too. And why don't you do this reaction? Give the organic product or products to the following reaction. And some of the more complex things we're doing this semester, because the structure is more complex. And I'll wait for everybody to finish. All right. So if we look at this molecule right here, it's really this reaction right here. Not with that arrow. What we have going on is this. Keep your eye on this carbon with two oxygens. The only thing that will change this hydroxyl group is replaced with this OR triple prime. Everything else stays the same. And this hydroxyl group is this hydroxyl group. This carbon is this carbon. Since things that are not involved in the reaction don't change, I can rewrite it. And the only thing that changes this becomes this. What's our triple prime? The carbon with the hydroxy group on the alcohol is the carbon this oxygen is bonded to. This reaction I will never give a synthesis problem on. Oh, let's do another one. This is fun. Like I said, please be patient. Hold on, I did something I shouldn't have done. And here you go again. Give the organic product or products for the following reaction. And let's be patient for everybody to finish. All right. If we look at this, this is the cyclic form of glucose. Acetal. This so happens R and our double prime are connected together. And what is this? What's different? Oh, hydroxy group on a carbon, alcohol, acid catalyst. Keep your eye on this carbon. Oops, I wrote it wrong. Now it's semi-acetal. And what's attached to that? R prime hydrogen, R double prime, OR stays. The only thing that changes is this becomes this. Therefore, what's not involved in the reaction, I can rewrite. Don't forget this bond, otherwise it's wrong. And now, what's our triple prime? This. And now, I did it wrong, sorry. It's a T-butyl group. And that's how you do this. Now, the question is, why am I going to all this trouble? Well, first of all, in case you wanted to write this down, I will be patient and wait. Give me a thumbs up when you're ready for me to move on. All right. Aren't I nice? Instead of just saying, all right, did you get it? Thank you, Charles. All right. What I'm about to write on the whiteboard, you do not have to copy down. Let's see something. Somebody just sent me a message. You're welcome. And please be patient. This is going to take a little while. Again, you do not have to write this down. Now, if you look on the board right now, you'll see the same molecule written 3 times. If I had a wider board, I would do another one, but you don't have to. Now, let's call these A, creative, aren't I? A, B, and C. Now, if we look at A, what do we have? This, the hemiacetal of the cyclic form of glucose. But now let's look at B. And on C4, this hydroxyl group is an alcohol. If I have an acid catalyst, look familiar? Keep on wanting to forget this oxygen. And this carbon is this carbon. This alcohol is this. And what happens? This goes here, and this should be R triple prime, and you form this new bond. Well, I'm going to do that. This oxygen bonds to that carbon. And again, all we're doing is this reaction, which I showed you in a simpler form right here, like we did here, except R triple prime is another cyclic form of glucose, and the alcohol is this alcohol. Now, if you look at B and C, once again, this carbon is this carbon. This alcohol is this alcohol. And, oops, wrong color. This forms that bond again. This bond right there. And if you look at C, if I had D, same glucose, it could link together. And what we're forming is a polymer of glucose in a cyclic form. And an easy way to write that is and they have a name for this polymer of glucose. What's that name? Starch. The next time you have a potato, rice, bread, French fries, pizza, whatever has starch in it, that's a polymer of glucose. And that all came about, first of all, that you could form the hemiacetal form of glucose, and then this unsymmetrical acetal formation. Now, if we look at this right here, and again, you don't have to write it down, what bond is between the two glucose? An acetal bond. And you learned about the acetals and ketals in test number 2. So let's look at something. Write the name or draw the structure, write the name of the product you get when you react 50 molecules of glucose with another 50 molecules of glucose with acid catalyst. Oh, let's see if you can get this. And the answer is starch. And like I said, Mother Nature is the greatest of all organic chemists. And putting all this chemistry together, you react glucose together to make starch, which is a major food group, also known as a carbohydrate, a polyhydroxyl molecule, ketone or aldehyde, or one that becomes one on hydrolysis. And we'll talk more about that. Now, switch is on. Don't write the structure down. I'll show you a better way. We talked about sucrose, table sugar. You should know fructose is glucose and fructose bond together. And here, the same thing, you form the acetal linkage from alcohol on fructose in the cyclic form and the glucose, which I just showed you. Now, what should you know about sucrose table sugar? By the way, this you should know. And let's look at sucrose. You should also know this. Sucrose, table sugar, it's a sugar because it's a disaccharide, or is a fructose bonded to a glucose molecule. You should know sucrose is fructose and glucose bonded together. And what kind of linkage is here? An acetal linkage. I think I'm going to sneeze or want to sneeze. I think I just stifled a sneeze. All right, so we now know that starch is many glucose molecules bond together in an acetal bonding or linkage. And we now know, or you know, because I already knew this, sucrose is fructose and glucose bonded together in an acetal linkage. And we call those polysaccharides. And this slide, you don't have to know the names. Monosaccharides bond together in glycosidic linkages, acetal or ketal. It's really mainly acetal. Now, starch is a polysaccharide, poly meaning many, saccharide, monosaccharides of glucose, the polymer. Now, the switch is off for amylose and amylopectin when the carbon number one with the aldehyde, or the hemiacetal that was the aldehyde carbon is bonded to the alcohol on carbon 4, we call that an amylose starch. When it's both number 4 and 6, which means it's branched, it's amylopectin. Switch totally off for that. Now, for test number 2, you learn the following reaction. If you take a hemiacetal or acetal or ketal and you react it with acid and water, you get back the aldehyde or ketone plus the alcohol you would have used to make that acetal or ketal. Now, what do you have in your stomach? HCl, H plus, acid. What do you have in your stomach? Water. What would be the product, and you can write the name or draw it, when you take starch and react it with acid and water in your stomach or anywhere else? I don't know, it's harder anywhere else, but why don't you think about that? Hint, what starch, what kind of bond? Write the name. All right, and the answer is glucose. And in glucose, the alcohol and aldehyde are connected together. And why is glucose the most abundant sugar in nature? Because all the starch you eat and all the animals eat are broken down to glucose. And that's why it's the most abundant. Let's try another one. Now, what would happen when you consume sucrose? What two products do you get? And I'll help you out. What is sucrose? All right. So what bond holds fructose and glucose together in sucrose? An acetal bond. And when you react it with acid and water, you get back the aldehyde and ketone you would have used to make that. Well, in this case, you get, doesn't matter which you put first, glucose and fructose. If I can spell it. So when you consume something where you put sugar in it or has sugar in there, sucrose, and I'm talking about that sugar as opposed to fructose, you make glucose and fructose. And this is something you should know. And it's just based on the chemistry you've already learned. Now, interesting thing, and now I'm going to brand it as such, this is my personal opinion. For a number of years, mothers groups have been complaining, and I justifiably so, that the high fructose content in various products sold to children, making it super sweet, is bad for them. And they claim that it causes autism and other diseases, even though they don't really have proof for that. I personally believe it's bad for them, but not because of the fructose. And the food companies have said, oh, we hear your pain. We're going to change a lot of our formulations. We'll cut back on the fructose and replace it with sucrose and still make it sweet. Well, guess what happens in this? Could you hold on 1 second? This is a very important phone call. Hi, everybody. I'm talking to my cardiologist nurse, something important. So I'm going to end class right now. I'll pick it up where we left off on Wednesday. I'm sort of all right, but I still need to talk to her. So I'll see you on Wednesday. Bye now. Gang gesund. Sorry about this.